Hi, I'm Mark Weitzman. Welcome back to Quantum Field Theory, A Student's Perspective. Today's lesson is a pretty short one. There's very little reading in the book, and I remind you again that this is a flip MOOC. You're supposed to do the reading before you watch this video. This lesson, lesson 4, is on the spin statistics theorem. Books have been written about this theorem. Most of you are already familiar with it. And what the theorem basically says is that when we have Lorentz invariance, quantum mechanics, causality, our theories are very restricted. And the end result is that this combination of quantum mechanics and relativity and causal effects leads to two kinds of particles: bosons, which have integral spin, and integral spin includes 0, of course. And then we have fermions, which have half integral spin. Now, for our purposes, what we want to discuss today and what this chapter is about is that when we quantize bosons, we have to use commutators. And when we quantize fermions, we have to use anti-commutators. And so the derivation and the Schrodinger treatment here in chapter 4 is very, very brief. But the derivation is really not that important. It's the result. So that's why I said this will be a very brief lesson. I will go over a little bit of the derivation. And I just want to make a note that you might remember chapter 1, where we talked about the Schrodinger equation. And we quantized the many-body Schrodinger equation, and we found out that actually we could have symmetric particles or anti-symmetric particles. I left out here that bosons are symmetric. And of course, fermions are anti-symmetric. This is probably the most complicated board ever for some very simple concepts. So what's important is that for the Schrodinger equation, we can have either symmetric particles or anti-symmetric particles. So doesn't that contradict our theorem? The answer is no, because this is non-relativistic. Doesn't meet Lorentz invariance. So just remember that. If you're dealing with a non-relativistic theory, you can have different things. Also, I watched a recent lecture, even for non-relativistic quantum mechanics, in 2 dimensions. There are some very interesting things that can happen due to topology. These are called anyons. And these are like different than bosons and different than fermions, but they only apply in 2 dimensions, 2 space dimensions. So, except when you're doing things with thin films and condensed matter or something, these don't really apply in quantum field theory. But you should be aware that there's an interesting topological effect in 2 dimensions only. Now, usually most textbooks, when they treat the subject of spin statistics, most textbooks, they reach this problem where they're doing the Dirac equation, And they, like Peskin and Schroeder, when they do the Dirac equation, which we haven't gotten to yet, we'll get to later, they try and use commutators, and then they derive an inconsistency. But in our book, Schrodinger is sort of deriving this inconsistency earlier with scalar fields. He's going to show that, and part of the 3-page derivation that he has here is to show that scalar fields have to be quantized with commutators. And if we try and use anti-commutators with scalar fields, you'll get an inconsistency. Just to remind you, the notation that Schrodinger is using is this. That is, he's using the minus on the bracket for the usual commutator and the plus on the bracket for the anti-commutator. More common notation is just to use squiggly brackets for the anti-commutator. Now, so Weinberg in his books naturally has like a complete treatment of this. And if you want to get the whole deal, read, I think, chapters 4 and chapters 5 of volume 1 and chapter 6 too of his book. And he does it in great detail. I want to start by just doing some derivations. If we look at equation 4.5, I'll write it out here, phi plus, the author defines some non-Hermitian fields, sort of like he's breaking down the scalar field into its components. That's equal to e to the I h0t phi plus x comma 0 minus I h0 t. This is equal to the integral of dk tilde e to the I kx ak. Now, the part from here to here is what I just want to show how it's done. He doesn't really show it. He does give the Hamiltonian, the free field Hamiltonian. See, this is just going from this is a Schrodinger operator at time 0, and he's time evolving it to a Heisenberg operator at time t. This is the standard. And he defines h0 as being the integral of d tilde k omega a dagger k ak. Let me check that. Yeah. And then there's the usual commutation relations, the only one that we're interested in. All the others are 0. So these are the standard commutation relations. And so I do want to, and he also defines the fields. The field, the Schrodinger field, So that's the Schrodinger field. And what I want to just point out is the plus means positive frequency field. And the convention in physics is that positive frequency has a time dependence of e to the minus I omega t. So this may drive you nuts. You see the minus sign, and yet we call it positive frequency. And like over here, remember we're using the East Coast metric convention. So this is e to the minus I omega t plus I k dot x. This is a positive frequency part, and he defines the negative frequency part similarly. Okay, so what we're going to do is we're going to, I'm going to prove this part here very simply, just because it's not in the book and maybe it was earlier in the problem. And then we'll go on to discuss some other computations. So I'll see you in the next video. Thank you.